Okay, so, have you done 3D graphing before? Okay, so, we're going to be doing a new type of graphing. So we did, what was the first new type of graphing you did? Parametric?
This year.
This year, yeah. So we did parametric graphing, which you hadn't done before. 3D graphing. Thankfully, it is relatively simple. Now, the complication is we are working on a 2D platform, and we have to make a 3D representation. So, anybody remember, like in grade school, you learned how to draw a cube? So you draw something like this. Or in geometry, you might have learned it. So you get something like that, you get a cube, right? 3 dimensions, looks sort of 3-dimensional. And the goal is we're going to be dealing with making 3-dimensional graphs on these graphs you have. Now, some of the things that are going to change, or that change with maybe dealing with 3D versus 2D. You hear the term quadrant. What does quadrant refer to? Okay, why is it called a quadrant? Yeah, it's got 4, it's got quad. When we deal with 3D graphing, instead of quadrants, we're dealing with octants. Because instead of just having this, how many parts? You've got 1 up here, 2, 3 on the top here, 4 on the top here, and then on the bottom, 5, 6, 7, 8. So the axis is divided into 8 parts instead of just 4 parts. Okay, you got the top on the top back here, the top, the bottom, that's 2, the top here, and the bottom here. We have the top here, the bottom here, top and bottom. So you see the 8, at least sort of anyway. Okay, so how about do with here? They got 1, 2, 3, 4, 5, 6, 7, 8. So this, as we see, this is a complication when you're dealing with 3 dimensions versus 2 dimensions. We're drawing on 2 dimensions, yet we need to represent 3 dimensions. Now, dealing with graphing, we started with ordered pairs, which gave us something like x, comma, y. When we deal with 3D graphing, yes, ordered triples. We get x, comma, y, comma, z. We might say the xy axes. Instead of just xy axes, we get the x, y, and z axes. Can you go up? Yes, I can. So, graphing it, one of the goals when you're doing graphing in 3D is to make it look 3D. And that's the complication. So, I'm going to pull up some graph paper on here. Let's see, do I have... I thought I had it in here, but apparently I don't have it there. Okay, so 3D graph paper. No, where is the positive x? generally when you look at graph paper, positive x is the one that's bottom left. Positive y is bottom right. And then positive z up. So let's say if we were doing the point 2, 3, 1. So we're going 2 in the x direction, so 1, 2, 3 in the y direction, 1, 2, 3, and up 1. You do an estimate. So basically, the easy thing is to do is to make some sort of representation to make it look more 3D. So I can do the runner.
Was that the answer?
The goal would be making sure it's clear you're talking about this point. So, and making it look like it is 3D. So if we say -1 to -3. Okay, first -1 in the x direction, so that's here. 2, 1, 2. I'm going to get rid of this. This is one of the reasons why you probably want to do each thing in a separate, in its own graph. Because trying to make it 3D can be a challenge. So now we're going down 3. 1, 2, 3. Because if I just made this point right here, is it clear that that's this point? Probably not. So the goal would be to give some sort of orientation to indicate this is a 3-dimensional point.
Where's the point?
Right here. So it's 1 that direction, 2 this direction, and 3 down.
So why is it not at the, why is it in the
It's just an estimate 1, 2. It actually probably, I think this paper is meant to do it like there. But this is the goal, is putting dots or something like that to help indicate and help make it look like it's 3 dimensions. Now, we're going to do vectors in 3 dimensions as well.
It should not. Do we do a lot of 3-dimensional in culture?
In what? Yes.
A lot?
You don't do much in the way of graphing, but you apply things 3-dimensionally. So let's see. 3, -4, 1. Again, we use the chevrons to indicate we're talking about vectors. Now we're talking 3-dimensional vectors. So let's see. 3 in the x, 1, 2, 3. -4, 1, 2, 3, 4, and 1. So our vector is going to go from here, straight line from here to here.
Oh, that's it?
But then we have to do, making sure it looks like it's 3-dimensional.
Does not look 3-dimensional. It is not.
But the goal, that's the goal, is do something to make sure it looks 3-dimensional. And it gets a bit more challenging. That is the big challenge of 3-dimensional graphing on 2-dimensional paper.
Oh.
Now, if you develop 3-dimensional paper, you can turn it in 3-dimensional paper to turn it in on. No, I don't know. I mean, I said you develop it. I have seen some.
Do they actually in Smart?
No, nobody said it this way. But basically, what you can do is, if you take a graph paper, this regular graph paper, and then tape onto it another graph paper this way, so you pull it down, but pull it back up, and it becomes 3 dimensions, and then have a way to indicate it's coming out of the 3 dimensions. Yeah, it's like a string on a like a toothpick or something like that. But I mean, you could construct paper that would go fairly well. However, it's a lot of work, especially for a lot of problems. If you're doing 5 problems, it would be quite a big hassle. The goal is make it look 3-dimensional. I didn't do a very good job with that one, but that is the overall arc. Now, other things we're going to deal with: distance. How does the distance formula work when we're dealing with 3 dimensions? So 2 dimensions is easy, right? What's the formula for distance in 2 dimensions? Yeah. So, everybody hear that? Or at least remember it? Now, if we're dealing with 3, so let's say I'm just going to go right here. What is that point? Okay, so -2, 1, 1. So let's say the distance from there to, let's just make it easy.
Can we just make it like that?
Like this?
Yeah. That's really helpful.
Maybe, honestly, I've got a couple different types. This is one that Mr. Sandvik gave me. I can grab my other one and see whether you like that more, but, and then this one, what's this point? Okay, and our goal is, what is the distance between them? So from here to here. How do you do it? Now, give it a couple ways you can deal with it. No. And what kind of triangle? Right triangle. So we can get to look at that. And if we combine that with, say, a triangle this way, so we can easily get this distance, right? What is it? Let's see, this is 3, this is 2, this distance would be square root of 13 across the bottom. And then how do I get the angle then if this is 1?
How would that be squared?
Okay, 3 squared plus 2 squared.
The right triangle.
Look at the red, and pink. Red, red, pink.
So where's the right triangle? On the right angle?
Right here.
That's right angle?
Yeah. Okay. So now look at the pink, pink, blue. How would you figure out the third side? So first we did square root of 3 squared plus 2 squared, right? That's where we got 13. How did I get this for this triangle right here? Huh? The blue part, yeah. Our distance, that's our final distance. Second theorem again, right? Which is just a distance formula, so root 13 squared is 1 squared. So we say square root of 13 plus 1. So no, this right here is square root of 13, right? So why, and notice this is 1 squared, why don't I just add 1 squared here? And that is our distance formula. So it is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So this is our calculate the distance between the two
I
points.
thought we had to do that.
No. No, this is a way you could justify that, but this is the actual
Which
formula.
one of them is right triangle? Can you go back?
Oh, both of them. The red one
Not
here
that one.
and the pink one.
How is that a right angle?
The right angle is right here on this part, going upward. Okay? And midpoint. How did you get the midpoint before?
X1 plus X2 over 2, comma, Y2 plus X1.
Over 2. Yeah. So what do you think you're going to do with 3 dimensions? Okay? just like 2 dimensions, x1 plus x2 divided by 2, comma, 1 plus y2 divided by 2, comma, z1 plus z2 over 2. So, basically identical to what we had with 2 dimensions, just adding our z component in. Now, unit vectors. Remember I talked about your I. The unit vector I is what? In 3 dimensions. 1, 0, 0, because it goes exactly 1 in the x direction. Vector J. 0, 1, 0. And we throw in vector K. And note, the rules for 2-dimensional vectors, all the rules still apply to 3-dimensional vectors. So if we were doing, say, 2, 3, 1, plus 5, negative 2, 6, what do I get? And order doesn't matter whether I add one before the other. As long as you do both of them, you're going to get the same answer. What about scalar multiplication? So if I had 4 times 2, 3, 0, what do I get? So scalar multiplication, again, works the same way. So lots of things are basically identical. But like I said, the hardest part is making something appear to be 3 dimensions when you're graphing in 2 dimensions.